Okay, imagine trying to recreate an entire planet from absolute scratch using literally nothing but math and code. Today, we're jumping right into this fascinating explainer where we track a developer's journey to do exactly that. We're going to look at the hidden logic behind simulating everything from the slow, massive crunch of plate tectonics to deep dynamic climate systems. So, how do you actually code an entire planet? Well, before we dive into the weeds, consider this. We aren't just looking at how to make some blocky Minecraft 2.0 kind of world. No, we're looking at how to build a truly accurate, procedurally generated globe using the actual rules of nature as our programming guide. It's like a giant mathematical puzzle. We'll be tackling this build in 5 phases. First, the digital sphere. Second, tectonics and continents. Third, forging the mountains. Fourth, simulating the climate. And finally, number 5, painting the biomes.
Let's kick things off with Phase 1, the digital sphere, creating the canvas. You know how flat digital maps often get super stretched out and weird at the poles? Well, to avoid that distorted terrain, the developer's very first step is creating a mathematically perfect sphere. By making sure every single surface point is the exact same distance from the core, they create a seamless, distortion-free canvas that makes it perfectly ready to be sliced up into manageable chunks and textured.
Moving right along to Phase 2, tectonics and continents, laying the groundwork. Now, to build realistic continents, you actually have to simulate literal tectonic plates first, which I think is absolutely wild. The developer starts by generating evenly distributed points across the globe, picking some to be the centers for major plates, which will eventually be our continents. Then, every surrounding point gets assigned to its closest center. But here's the really clever part. In the real world, minor plates don't just sit perfectly inside major ones, right? So they specifically coded minor plates to spawn strictly along the borders of the major plates to perfectly mirror reality. Okay, so you know that harsh, jagged static on an old TV? That's standard random noise. Perlin noise, on the other hand, is more like rolling hills. It generates random values, sure, but with smooth, natural transitions instead of chaotic, jagged jumps. By assigning a Perlin noise value between 0 and 1 to every single point on our sphere, it gives our digital plates and future continents these beautiful, sweeping borders instead of just jagged static. And right down the middle, that 0.5 mark acts as our ultimate digital sea level. Boom! Instantly, our oceans and land masses are separated. Any point with a Perlin noise value above that 0.5 cutoff, that becomes land. Anything below it simply sinks into the digital ocean. After that, the developer runs an edge detection algorithm to smooth out the rough coastlines, making the whole thing look incredibly natural. But obviously, real terrain isn't just perfectly flat. To give it that natural variation, the developer stacks 4 different octaves of this Perlin noise on top of each other. Think of it kind of like painting. You start with the broad strokes, that's the base continent shape, and then you layer on large hills, small bumps, and finally fine surface details. Each subsequent layer adds amazing complexity, but has a progressively smaller influence on the overall shape. It gives us everything from rolling plains to highly textured rocky outcrops. That brings us to Phase 3, forging the mountains, when plates collide. This all comes down to mathematically measuring the stress level of each point based on how those tectonic plates we just mapped out are moving. At convergent boundaries, plates are literally crashing head-on into each other. That immense stress forces up towering mountain ranges and carves out deep ocean trenches. But at divergent boundaries, plates are actively pulling apart. That gap releases magma from the planet's core to birth volcanoes. By calculating these exact stress levels, the simulation naturally places mountain ranges right where plates logically collide. It's exactly how the Himalayas formed here on Earth. Okay, Phase 4, simulating the climate, adding weather. Now that our rocky terrain is locked in, it's time for the atmosphere, and it all starts with one very specific, almost magical number, 23 degrees. By programming the digital planet to tilt at exactly 23 degrees, mimicking our actual Earth's rotation, the entire mathematical framework falls into place. This exact tilt makes the temperature realistically drop off as you travel from the hot equator out toward the freezing poles. But, temperature isn't just about latitude. It's a highly dynamic calculation. It starts by measuring the distance from the equator and factoring in the strength of the planet's sun. Then we apply our trusty Perlin noise again, just so our temperature zones aren't these boring, unnatural straight bands across the globe. Finally, altitude gets factored in, so it genuinely gets colder as you climb up those newly forged mountain peaks. So what about rain? Well, precipitation naturally peaks at the humid equator, rapidly dips down to create dry deserts, and then gradually rises again as you move further out. Interestingly, with a little help from AI, specifically ChatGPT, the developer crafted a really complex math function to perfectly simulate this global rainfall dip. It's the exact same natural mechanic that places the Sahara Desert exactly where it is on Earth. Our digital deserts are forming mechanically, not just arbitrarily placed by a programmer.
And finally, Phase 5, painting the biomes, bringing the world to life. For our final layer, the underlying logic is honestly just remarkably elegant. Every single point on our digital sphere is checked against a simple matrix. If a coordinate has a high temperature and high precipitation, the system automatically spawns a lush tropical rainforest. High temperature but really low rainfall? You get a desert. Match a low temperature with low precipitation, and boom, you get a polar tundra. It's literally matching the specific heat and moisture of every single coordinate to seamlessly generate the correct living ecosystem. And there's one final, really beautiful detail here. If the simulated temperature dips too low, the generated water actually freezes. This procedural rule automatically caps our completely simulated globe with natural, icy poles. It finishes off the entire ecosystem purely through the elegant math we've set up from the start. Which brings us to a pretty profound question. If we can mathematically simulate an entire living Earth from a totally blank digital sphere, what other complex systems in our universe are just waiting to be reverse engineered? This explainer really shows the immense power of procedural generation. It proves that by stacking simple, natural rules layer by layer, you can create infinite complexity. It's a fascinating thought about the hidden math dictating the real world all around us. Thanks for exploring this incredible digital world with me.